Hello, I'm Srđan Šumarac and I'm a PhD candidate at the Translational Neurophysiology and Brain Stimulation Lab here at the Krembil Brain Institute, led by Dr. Luka Milošević. So the brain is a remarkable organ that communicates through bioelectric signals, which are tiny electrical pulses that drive everything from movement to speech and thought. However, when these signals become disrupted or imbalanced, it can affect normal brain function. At our lab, we not only measure these patterns, but we use neuromodulation to deliver precise pulses back into the brain to help correct and restore this balance. One of the neuromodulation techniques that we use is called deep brain stimulation, or DBS for short. Think of it like a pacemaker for the brain. Surgeons implant thin wires into specific areas of the brain and connect into a small battery pack under the skin near the chest. This system delivers continuous electrical stimulation to help relieve symptoms of various neurological conditions. Our team is in the operating room for every DBS surgery at Toronto Western Hospital. We monitor brain signals in real time during the procedure to help guide the electrode to the sweet spot, which is the exact location where stimulation provides the most benefit with the fewest side effects. A powerful example of how transformative DBS can be is demonstrated by CBC journalist Harry Forstall. After living with Parkinson's disease for several years, he underwent the DBS procedure with our team in 2022. As you can see here, when DBS is off, his symptoms make everyday life difficult. But when he turned stimulation on, his symptoms noticeably improved. He returned to broadcasting shortly after, calling the procedure truly remarkable because it gave back his independence and hope. But here's the catch. Current DBS systems run non-stop. Once they're turned on, they stimulate the brain 24/7, even when symptoms aren't present. That's like leaving your house lights on all day, even though you're not home. So one of our lab's primary and major goals is to make DBS smarter. We're developing something called a brain-computer interface, or BCI for short. This system listens to the brain's activity and only sends stimulation when it's actually needed in just the right amount. For Parkinson's, for example, we imagine a system that detects brain activity linked to symptoms such as tremor. Then, when a tremor is about to happen, it ramps the stimulation up during that window and turns it back down when the brain calms down again. To show you how a BCI works in a fun and simple way, my colleague Antonio and I have put together a short demonstration. Here you will see how it's possible to use my own brain activity to control Antonio's wrist. First, Antonio places EEG electrodes on my head to record my brain's electrical activity. Then I stick small stimulation pads to the muscles in his forearm that will be used to deliver light electrical pulses that cause his wrist muscles to contract and flex. Now, when I concentrate on moving his hand, the system reads my brain signals, decodes them, and sends the command to stimulate the muscles. To make this interesting, Antonio is blindfolded. He has no idea when I'm thinking about moving his wrist. But after a few seconds of focus, you'll see that his wrist suddenly flexes. That's my brain moving his hand in real time. This is a non-invasive, simplified version of what a BCI can do, but it captures the core idea, which is a system that listens to the brain and responds when the time is right. Our team is actively involved in developing and testing new algorithms in the operating room with the goal of making DBS technology more intelligent and more personalized. We're just at the beginning of what BCIs are capable of, and every step forward is about giving people greater control, lasting relief, and the chance to truly reclaim their lives.